Thank you very much. Good afternoon, everybody. Hopefully you're not too tired yet. All right, so imaging of the surface of exoplanets, isn't it a dream? Isn't it that what we want to see, the surfaces? So I will address two questions. Can we do that? Can we see the structures on the surfaces? And finally verify all those beautiful artist impressions of exoplanets? And second question is that if we can, how can we actually detect life? And would it help us to see the structures to detect the extraterrestrial life? How we can test that? We can, of course, as we discussed, we have one example, one data point is Earth, and we can test everything on Earth life, on Earth, how we see Earth from space and from afar. So we used observations of NASA Earth Observatory, where we have taken some maps of real observation of the Earth, and we start from Albedo maps. So there is a bunch of those maps, and Albedo maps are quite useful. So this is a map here presented as an example for March 2003, just randomly kind of selected. And we have an exercise. I'll show you an exercise of this map. So if we look at a planet, we've covered this by continents and oceans and variations of the albedo, and that planet rotates around the axis as we see it on the Earth, on other planets as well. Then variation of that albedo map I showed you before will produce the reflection light curve like this, not very much informative, one can say. And if we do kind of inversions of this light curve, we get a bright blob and a certain place on the planet and see no much details. But now, if we look even further away from afar, then we can see planet reflecting light of the star at different orbital phases, like we see it on Venus or Mercury from the Earth. We can actually see variations of that light curve at different illumination phases. And that inversion of this light curve actually would help us already to see some details on the planetary surface. And we used this technique for a similar technique for mapping stellar surfaces before. As we know, stars see also as point-like sources, and we learned quite a bit about star spore distribution and evolution of these stars. And we'll now apply this technique or similar technique for inversion of the light curve of the exoplanetary surface. So we'll take this map, which I showed you before, albedo map, and we'll transform it into a situation that we see this exoplanet at a certain geometry on an orbit around the star. So here these parameters are given for the inclination of the orbit, 60 degrees, 30 degrees, and inclination of the rotational axis of the planet towards us also is 60 degrees. So all these geometrical parameters with the orbital period equal to 60 rotational period of the planet, so that we can generate about 3,000 points on that light curve. This is kind of dream light curve with the signal to noise 200, but say, okay, this is maybe the best case, or maybe not so realistic, but probably couldn't do better. What can we get? So you see, on the top, this is our input map, original one, and at the bottom is the recovered by this inversion technique map. What we can see is that about 90% of the high contrast features, such as continents, are recovered with the standard deviation about 10%. So that accuracy of 10%, I haven't seen better for these inversions. Usually it's between 10 and 15% accuracy what we can get. We can get pretty good picture of high contrast albedo, such as structures such as continents in contrast to the dark ocean. So now, another example is if we just put it upside down. You know, there's the south up inversion when we see Antarctica on the top of this map. And the continents inverse. So for those who are from Australia, it looks very familiar. For us who live in the northern hemisphere, it's upside down. So that upside down kind of inversion also works pretty well. And it's amazing, also, of course, that Antarctica is a high contrast feature on the map. It's recovered pretty well. And it's actually, on other planets, we've seen that there are ice-covered poles. So that feature, very bright feature, roundish kind of at one place, would also indicate the position of a rotational pole of the planet. So even if we are kind of a little wrong in first estimate of the inclination of the planet, we can figure out from that stable high albedo feature that it could be an ice-covered pole of the planet. So now if we go to a case where we reduce amount of data, go to more realistic scale, still with the signal-to-noise 200 here, but significantly less data points, you see that, of course, the map gets fuzzier, the contrast gets a little less, but still the standard deviations between input and output map is 11%, it's higher, but still reasonable. So still the large-scale land masses can be very well distinguished, and albedo is underestimated compared to the small-scale features on the input map, but on average we can say that this could be the continents embedded into ocean. Now, if we go to low signal-to-noise, which is even more realistic for exoplanets, that we can collect signal-to-noise 20 in this case, you can see that the continents become even fuzzier, but still the major landmass is still very well recovered, with even some hints of Australia and South America here visible near the edge. So what are these are the perfect inversions for perfect planet without clouds. And if we look at the Earth from the space, we see that actually seeing Earth without clouds never happens. So there are a lot of cloud noise. Plus there is seasonal variations, cloud variables, the seasonal albedo variations. We also heard this discussion in the morning about possible variations due to life activity. Plus, there is ice coverage variations on the surface. All this introduces additional noises, and I don't show it here, it's too much to show, but we've done this test, and we see fuzzier contours of the continents, but it's still recoverable. So at the level, what I showed you before, at this signal-to-noise 20, basically that is a good illustration if you have variations due to natural changes in the planetary conditions, either seasonal variations or cloudy variations. So this, or a little better than this, you can get as a result. So now Proxima b is most probably tidally locked, not necessarily, but could be. And how this will work for planets like this. So now we have several, these are realistic orbital parameters for Proxima b, and the rotational period is 11.2 days with signal-to-noise 100, but observations are taken over the several orbital periods, which is possible on a reasonable timeline. We can get, this is the restoration map you can see, recovered map. So the continents are still there, can be recovered. The advantage to observe it different rotational or orbital periods, actually collecting information over many periods, is that you can slightly shift in phase, so that will increase your spatial resolution. And also observing on the same phases, but collecting data, of course, you increase in signal to noise. So that helps to restore the large land masses on the planet. So if this planet is not tidally locked, and there is some discussion that it could be in a 3-to-2 resonance, then the period would be 7.5 days as compared to orbital period 11 days. Then we'll see for these two different, so we see two different sides, two different rotations, and you see these two peaks are repeatable here on the plot. Again, over about 20 rotational orbital periods, we can get information which is a little better than the previous case. So even this resonance orbit helps to get some more detail in the map. And this technique also allows us to in addition to resolving the surface feature on the planetary surface, we can also look at the parameter space. Actually, we can minimize the inversions towards parameters and retrieve the parameters such as orbital inclination, azimuth of the orbit, and planet inclination. And from direct imaging, of course, we can figure out if we resolve the system, we can figure out inclination of the orbit, but inclination of the planet won't be actually seen so easily. And so this combination of orbital and planet inclination can be disentangled through this inversion technique as well. So now, as we resolve these signatures of the continents, we can see the continents on planets. Can we see the biosignatures, and in particular photosynthetic biosignatures? What if there are colonies of photosynthetic bacteria or maybe vegetation similar to us, which is improbable maybe, but in a way also possible. So this is a kind of synthesized planet with the continents having a little bit of green stuff and deserted parts of the continent and as an input. And we can observe that, if we can observe that planet in different bands, for instance, here is shown in pink, this is infrared, in red, this is red band, and then in green band and the blue band. So it's basically, these are RGB bands which we have on our iPhones plus the infrared camera. So you can see on the top this input and at the bottom the recovered map. So we can do inversions on these different bands in 4 different bands, and we can get composite this RGB image of a planet. So this is a photograph of a planet from afar compared to what we put in. So there is, again, this overall structure of the continents is recovered. This is the case, actually, for light curves, the best one I showed in the beginning. So this is the best case observation situation. But nevertheless, it's interesting to look what we can do in the best case. And here, we can see again these continents, and we can see also that we can distinguish between these vegetation-covered areas and somewhat deserted area. Now, if we since we resolve these features, we can look at the spectra, and we have four bands measurements. 2 infrared here are the same, basically. So you can actually, on resolved features of that planet, you can average out parts of the surface and compare the spectral information on the input and the output. And here the spectrum shows in the line, this is input and crosses this, this is the retrieved image. You can see that actually in this RGB plus infrared band, the signature of the green vegetation is clearly visible. So we can recover that on surfaces of other planets if we have enough observations, as usual. So, but this is pretty reasonable. So now, so that signature is corresponding to the chlorophyll absorption, and we've shown that this absorption is polarized, and if we add polarization on top of these photometric measurements, we can increase also the contrast of the detection. So now with this signal to noise, which I said 100 or 200, when we are successful, how large telescopes should be to, first of all, to resolve this system, and second is to actually collect enough signal to noise. And this calculation shown for Proxima B with the best coronagraph performance at the sphere at VLT for 1 hour integration time at full illumination and albedo, average albedo 1.3. So with all these parameters, we see that actually we need telescope of a 20-meter size or larger. And that telescope not only has to be large, but it has to be also high contrast. So we propose is using the off-axis telescopes, which are allowing the radio observations. You have seen these pictures of the telescope shown before. So allowed unobstructed collection of the photons from the object and then directing it to secondary mirror and immediately get the highly stable photometric or polarimetric signal measured. So one of the first telescope which is now under construction in our set is a so-called Planets telescope, from the abbreviation polarized light from the atmospheres of nearby extraterrestrial systems. This is 1.85 meter telescope as a pathfinder to larger telescopes which are extremely photometrically stable. So the next in this series, when we combine several off-axis telescopes in one array, in this case, as a ring, we call this system ExoLive Finder, since this system will be able to obtain the required, this is about 20-meter size, what I said in my graph, this system will be capable of imaging of Proxima B surface with the technique I have shown, and a couple of dozens of nearby exoplanets as well. So that is a combination of interferometry and coronagraphy with optical off-axis telescopes allows us to achieve sensitivity, contrast combination of this coronagraphy and interferometry on the mirrors of the telescope allows to achieve the contrast of this in the dark spot, which is shown here on this PSEF diagram, of several orders of the magnitude deeper than the continuum. So that you see the at least 6 or more orders of the magnitude can be darker than the rest. And once we have that, we can combine in a larger system called Colossus with about 60 mirrors combined in a single array. And that system will be able already map the surfaces of hundreds of exoplanets in the solar neighborhood. And in addition, once we have the system, we go to the SETI programs as well. We can do search for intelligent life as we become sensitive to variations of the, if we measure infrared variations of these planets, we become sensitive to so-called heat islands, which we have on the Earth as well. Like shown here, these large cities are about 10 degrees Celsius hotter than the surrounding environment, and civilizations similar to us using similar amount of energy and clustering in orbit-like areas, it will be possible for us to detect with this system. So this is also projection for the future. So here's my conclusions, and yes, we can resolve indirectly the surfaces of the planets. We can see oceans and continents. We can actually, once we resolve it, we are not anymore suffering from this integrated light. How can we actually decide whether there is life or not in this integrated signal? We can look precisely at different places on the planets and analyze spectra from these different places. And biopigment polarization will help us to actually increase the contrast of such detection. Thank you.
Thank you. Sorry. Actually, I probably have time for one question. Yeah. So, Jerry, you had your hand up first.
Hi. How would the weather on Earth have it impact these measurements? How much longer would you have to observe in order to get the same kind of results?
Right. So our model shows that, in principle, when you do these 3,000 measurements in the cloudy atmosphere, so what I've done is that we take the cloud from this NASA webpage. You can get also cloud coverage. So we take monthly coverage, put in monthly albedo maps, and you just run it through the year, which is collecting 3,000 points over the year. You see some patches of the continent, and you see like a background of this of the clouds. So definitely the cloudiness can be a big obstacle in general, like on Venus as an example. We never see the surface until we send the probes or we do radar measurements. So Proxima b may happen just a cloudy planet, and that's what we will find out as well. And our technique actually allows to see whether it's clouds or not. So that is also possible. The signal, modulation signal is reducing. So in the end, if it's homogeneously cloud, you see the smooth signal like you would see no features on the surface.